We're going to start with Sebastien Garmier from Switzerland.
Hello, my name is Sebastien, I'm from Switzerland, and I created images of black holes. So basically, in high school, I had to choose a project that I would do for a year, and I chose to do a simulation of general relativity. General relativity is Einstein's theory of gravity. And essentially what it says is that gravity is not a force between objects, but rather a consequence of curved space-time. So to illustrate what curved space-time means, I've brought an apple, and what better way to illustrate gravity than with an apple? So imagine an ant living on that surface of that apple. And now further imagine that ant moving always straight. Because the surface of the apple is curved, after some time the ant will actually get around and be at the same place again. So locally the ant is moving straight, but globally the path of the ant is quite curved. So the same thing happens with falling objects in space-time. Everything that is falling under the influence of gravity will travel straight locally, but globally will follow a curved path. And light is no different, so light also follows curved paths through space-time. It's just that this effect that light is being bent by gravity is quite weak. If we make the gravitational field very strong, however, the effect becomes very pronounced. So one way to get a very strong gravitational field is using a black hole. So a black hole is a region of space-time where gravity is so strong that nothing can escape from it. And just outside of a black hole, gravity is strong enough to deflect light very strongly. So I guess black holes are round, roughly, and that apple is quite round as well. So I'm going to use the apple now to mean a black hole for the rest of the talk. So black holes have three properties. They have a mass, they have an angular momentum, which tells you how much they spin, and they have an electric charge. And this model with these three properties is called the Kerr-Newman model of a black hole. So as you can see here, this is a schematic of how light is being deflected by a black hole. You've got a black hole in the middle, and you've got a light source on the right, and just two light rays are indicated in red. As you can see, they are being attracted by the black hole, and they arrive at the observer O on the left-hand side. And that observer sees two light rays arriving from two different directions, and they have the impression that there are actually two sources of light, even though there's only one light source. And you can just imagine how interesting that becomes if you look at it in three dimensions. So I figured, what would a black hole look like if you could actually look at one? And so what did I do? I programmed a software called Q-ray, which stands for CUDA Relativistic Ray Tracer, that is capable of calculating images of black holes. So how do I calculate images of a black hole? So imagine I'm looking at this black hole, and I've got light rays hitting my eyes from all sides. So what the software now does is it follows each of those light rays backwards until the source of the light ray is found. Then basically one light ray corresponds to one pixel. I found the source of the light ray. I can call it a pixel accordingly. This is how the image is created. This process of following the light rays backwards is called ray tracing. To make calculations a bit more quicker, I used CUDA, which is a technology that allows me to do calculations parallelly on the graphics card of the computer. Right, and so that's why the name is CUDA Relativistic Ray Tracer. So let's look at two images I've created with my software. On the left, we have a black hole with a ring. So imagine a ring around this apple, like the planet Saturn. And the front side of the ring, so this part here, is quite normal, like you'd expect, but the back side is kind of weird. And that's because light from here, from the back side of the ring, can actually come over the black hole, come back down, and I see it as light coming from above. So that's the top part of this arc. Then I also have an arc on the bottom, and that's just the lower side of the disk of the ring. Light goes down, it's bent upwards, comes to my eyes, you can see both sides of the ring at the same time. Then on the right, you have a different situation. Well, actually, it's quite similar. The only difference is that the black hole is spinning now, and the spinning black hole drags space-time around itself. So on one side, light is kind of accelerated. On the other side, it's kind of slowed down. That's why the image becomes asymmetric. This is also an image from my software. It's a very beautiful one. It's a starry background with a black hole in front. And you can really see how interesting phenomena occur when strong gravitational fields are present. So in conclusion, what's the software good for? Well, it turned out that my software ended up being quite easy to use. You can just play around with the parameters, see what comes out. So it's a quite nice tool for educational purposes. But of course, it's also easy to predict what a black hole would actually look like. Thank you very much.
Thank you very much. Do we have any questions? Yes. You're going to get a microphone. Great, thanks.
Hello. Does light revolve around the black hole like the Earth would do around the sun?
Yes, there's actually the possibility that light can get into orbit if it gets sufficiently close. This is called the Photon Sphere. It's a certain distance away from the black hole. Light just keeps turning around the black hole. Yeah.
And if you enter that field, if it would be possible, would you be able to see things from the past? And
well, you'd be able to see all that light that has been in there in that orbit. So maybe you'll see light that is 1,000 orbits back or 1,000,000 orbits back. So yeah, you could potentially see things from the past if you're at that specific location in the Photon Sphere, yes.
That's really cool.
Yeah.
Any other question? Yeah, up there.
I'm just wondering if the software is available anywhere.
Yes, it is. So if you Google Q-ray, CUDA relativistic ray tracer, you can probably find it. It's also on my website, sebastiengarmier.ch. It's just my first name, last name, .ch. I think you have my name in the brochure. So, yeah.
Thank you.
It's freely available. Everybody can download it. Also the source code. If you want to modify it, it's open source.
All right, any other question? Okay, then we're going to move on. Thank you very much.
Thank you.
Okay.